Imagine a scale so vast, your mind struggles to truly comprehend it. This isn't hyperbole, it's the honest truth of a cosmic titan, residing more than 1 billion light-years distant, silently navigating the deep dark. It holds more stars than you could ever count in countless lifetimes. You might believe you already grasp the immensity of the universe. Perhaps you've seen images of our Earth, a tiny blue marble next to Jupiter's stormy expanse. You've heard the Sun could comfortably contain 1 million Earths within its fiery embrace. You might even know our own Milky Way galaxy stretches across 100,000 light-years. But every comparison, every mental shortcut you've ever used to understand cosmic dimensions, begins to unravel when astronomers reveal what lies far beyond our galactic neighborhood. To embark on this journey, more than 1 billion light-years into the profound depths of space, we must first establish a familiar footing. We need a point of reference that our minds can anchor to, and the only scale we truly comprehend is the one we inhabit. Start with Earth. Our planet feels immense to us. Its oceans span horizons that seem endless. Continents require hours, even days, to cross by aircraft. Mountains ascend for kilometers into the heavens. Yet, Earth is tiny. 1.3 million Earths, approximately, could fit inside our Sun. The Sun itself feels colossal, it dominates our sky, holding 99.8% of all the mass in our solar system. Every planet, every moon, every asteroid and comet, orbits its gravitational center. Its pull binds everything together. But even our Sun, so mighty, is just an average star. Stars exist that are far, far larger. Some are so gigantic that if one were to replace our Sun, its surface would extend far beyond the orbit of Mars. A select few would even engulf Jupiter whole. Compared to these stellar behemoths, our Sun is truly modest. But stars are merely the beginning of the cosmic hierarchy. Our Sun is just one of hundreds of billions of stars nestled within the Milky Way galaxy. When you gaze up at the night sky and observe that faint, cloudy band stretching across the darkness, you are witnessing the combined light of countless distant stars. They are packed so densely along the plane of our galaxy that their individual gleam blurs into a continuous glow. The Milky Way spans about 100,000 light-years from one edge to the other. This means light, traveling at an astonishing speed of 186,000 miles per second, would still require 100,000 years to traverse its full width. To truly grasp this number, consider this: modern humans have existed for roughly 300,000 years. If a beam of light began its journey across our galaxy when the earliest humans first appeared, it would only now be nearing the far side. Our galaxy contains somewhere between 200 and 400 billion stars. Orbiting many of these stars are planets. Orbiting many of these planets are moons. The Milky Way is not a mere scattering of lights in empty space, it is a vast, rotating city of suns. And yet, as enormous as it feels, the Milky Way is not unusual. Just 2.5 million light-years away, its twin, the Andromeda Galaxy, resides. It is slightly larger than ours and may contain perhaps 1 trillion stars. On a clear night, far removed from the city's glow, you can actually perceive Andromeda with your naked eye. That faint, hazy smudge in the sky is an entire galaxy, a universe of stars unto itself. For the majority of human history, this fact remained unknown. People once believed the Milky Way encompassed the entire universe. They thought the stars above were fixed lights embedded in a grand cosmic sphere. The hazy band across the night sky was an enduring mystery. Ancient civilizations imagined it as spilled milk, a celestial river, or even a pathway for departed souls. It wasn't until the early 20th century that astronomers, looking through ever more powerful telescopes, realized those faint smudges were not mere clouds within our own galaxy, but entire galaxies, separate and distinct. That revelation shattered our previous sense of cosmic scale. Suddenly, the universe was not a single galaxy. It was billions. Today, astronomers estimate there might be as many as 2 trillion galaxies within the observable universe. Each of these galaxies holds millions, billions, or even trillions of stars. And galaxies themselves are not randomly scattered throughout the cosmos. They gather, drawn together by the invisible hand of gravity. Our Milky Way, for instance, belongs to a modest collection known as the local group. Several dozen galaxies, all bound by their mutual gravity, drift through space as a vast, cosmic family. These groups, in turn, gather into larger structures called clusters. Clusters then aggregate into even grander superclusters. On the very largest scales, galaxies aren't scattered like dust, they trace out enormous, glowing filaments. These filaments form a colossal cosmic web that stretches across billions of light-years. If the universe were a three-dimensional map of luminous threads, galaxies would be the glittering beads strung along those threads. This intricate, interconnected environment is precisely where cosmic giants are born. Most galaxies are modest in size. Many are dwarfs, containing only a few billion stars. Some are irregular, pulled and twisted by violent gravitational interactions. Spiral galaxies, like our own Milky Way, are a common sight, admired for their graceful arms and elegantly rotating disks. Then there are elliptical galaxies. Ellipticals are smooth, rounded systems, predominantly populated by older stars. They lack the dramatic spiral arms characteristic of galaxies like ours. Their stars orbit in complex, scattered paths, rather than within a flat disk. And at the very centers of the largest galaxy clusters, something truly remarkable unfolds. Gravity relentlessly pulls everything inward. Imagine an immense valley, invisibly carved by mass itself. Over billions of years, galaxies slowly roll downhill toward the lowest point of this gravitational well. As they fall inward, they collide and merge. The biggest galaxies grow ever larger by relentlessly absorbing smaller ones. This process, slow beyond human comprehension, can take hundreds of millions of years for a single galactic merger to complete. Two galaxies approach, stretching into long, ethereal tidal arcs. They swing past each other, then slowly, majestically, spiral together. Stars rarely collide during these mergers, the distances between them are simply too vast. But gravity reshapes everything. Gas clouds are compressed, igniting furious bursts of new star formation. Central black holes feed ravenously, blazing with intense energy. Existing structures are torn apart and then slowly, painstakingly, rebuilt. Over immense spans of time, spiral arms are destroyed. Order dissolves into chaos. And from that chaos, something larger and smoother settles into place. This is the ancient mechanism by which the most massive elliptical galaxies are forged. Not in a single, sudden event, not in a brilliant flash, but through layer upon layer of cosmic history, built across eons. Our own galaxy is actively participating in this cosmic dance right now. The Milky Way is gradually absorbing smaller dwarf galaxies. Streams of stars arc across our night sky, silent remnants of galaxies that ventured too close and were torn asunder. And in approximately 4 to 5 billion years, the Milky Way and Andromeda are destined to merge. Two vast spiral galaxies will collide, their structures intertwining, eventually settling into a single, larger, elliptical galaxy. This is not a rare occurrence, it is the normal, predictable story of cosmic evolution. But sometimes, under precisely the right conditions, this process extends far, far beyond the ordinary. If a galaxy finds itself situated at the exact gravitational center of a particularly rich cluster, it transforms into the ultimate collector. Over billions of years, it absorbs galaxy after galaxy after galaxy. Its halo expands, its stellar population swells to unimaginable numbers. Its central black hole gains immense mass with every single merger. The universe builds from the bottom up. Small structures form first. They merge to form larger ones. Larger ones merge to form giants. And at the extreme, almost incomprehensible end of this cosmic hierarchy, beyond the scale of galaxies like our own, beyond even the titanic size of Andromeda, lies something that challenges our ability to visualize it at all. A galaxy not hundreds of thousands of light-years across, but millions. A galaxy not containing hundreds of billions of stars, but tens of trillions. A galaxy that sits at the very heart of a massive cluster, like a gravitational emperor, having spent billions of years consuming its surroundings. Before we name it, before we measure its astonishing dimensions, before we even attempt to fully comprehend it, pause for a moment. Everything we have described so far, our Sun, the Milky Way, Andromeda, entire galaxy clusters, already stretches human imagination to its absolute limits. And yet, all of that is merely the stepping stone. Because what we are about to examine is not just another galaxy. It is the largest galaxy humanity has ever discovered. And compared to its staggering immensity, even the Milky Way begins to feel remarkably small. More than 1 billion light-years from Earth, nestled within the constellation Virgo, lies a prodigious gathering of galaxies known as Able 2029. Through the lens of a powerful telescope, it appears as a densely packed patch of faint, shimmering light. Dozens of galaxies, all bound by an unseen gravitational embrace, slowly orbit a shared, mysterious center. And precisely at that center, an extraordinary entity resides. Astronomers refer to it as IC 1101, though the designation itself offers no hint of its true, astonishing nature. When first catalogued, it registered as little more than a dim, indistinct glow. There was no way to conceive, at that time, that this faint smudge would one day be revealed as one of the largest galaxies ever discovered. This central galaxy stretches between 4 and 6 million light-years from edge to edge. To place that into staggering perspective, the Milky Way, our own home galaxy, is roughly 100,000 light-years wide. Already, that figure feels unimaginably vast. Yet, this giant is 40 to 60 times larger in its sheer diameter. If our entire galaxy were somehow reduced to the size of a coin, this titan would span the entire length of a substantial room. Were it to occupy the Milky Way's position in space, it would not merely swallow our galaxy whole, it would also engulf Andromeda, our closest large neighbor, without effort. The entire local group, a collection of dozens of galaxies spread across millions of light-years, would comfortably fit inside its immense structure. And size is merely the beginning of its wonder. This galaxy is estimated to contain around 100 trillion stars. By comparison, the Milky Way, at its very maximum, may hold a few 100 billion stars. This means a single galaxy, IC 1101, could host hundreds of times more stars than our entire home system combined. If you attempted to count them, steadily, at a pace of 1 star per second, without a single pause, the task would demand more than 3 million years to complete. 3 million years ago, early human ancestors were just beginning to walk upright on Earth. And yet, what we are observing is not this object as it exists today, but as it was more than 1 billion years ago. The light reaching our telescopes departed its stars long before complex life forms even appeared on Earth. While evolution slowly unfolded its intricate tapestry here, those ancient photons were tirelessly crossing the immense emptiness between galaxies. Only now, after their epic journey, have they finally arrived. This galaxy is not a graceful spiral like the Milky Way. It is an elliptical galaxy, smooth, rounded, and devoid of the elegant, sweeping arms we associate with classic galactic images. Its stars orbit in myriad directions, rather than concentrating within a flat, rotating disk, lending it a more uniform, often featureless, appearance. Elliptical galaxies are often ancient, their brightest, hottest stars having burned out and faded long ago. What largely remains are older, redder stars, stellar elders that have been faithfully shining for billions of years. This fits the picture perfectly here. Despite its immense size and astonishing number of stars, this cosmic giant is remarkably quiet. New stars are forming only rarely within its vast expanse. The necessary gas, the raw material required to fuel stellar birth, has mostly been consumed or heated beyond the point of usefulness for collapse. This naturally raises a crucial question: how did something this unfathomably large form in the first place? The answer lies precisely in its strategic location. Sitting at the gravitational heart of Able 2029 grants this galaxy an unparalleled advantage. In clusters like this, gravity inexorably pulls smaller galaxies inward over billions of years. As they drift closer to the cluster's center, escape becomes an impossibility. When a smaller galaxy ventures too near, it is slowly, brutally torn apart by the immense tidal forces. Its stars are stripped away, one by one, and added to the ever-growing larger system. Its gas is absorbed, its central black hole eventually merging with the dominant one at the core. This process, often called galactic cannibalism, has likely occurred again and again. Over billions of years, dozens of major galaxies may have been consumed, along with countless smaller ones. Each merger added monumental mass. Each collision erased old structures. Each event contributed to the immense scale we observe today. It sounds violent, but it is simply gravity, acting relentlessly over colossal spans of time. With every merger, any original spiral structure was obliterated. Stars were scattered into new, complex orbits. Order dissolved into chaos, and that chaos eventually settled into the smooth, rounded form we witness. What we see today is the ultimate result of that long, epic history. And there is something subtly surprising about it. For all its staggering mass, for all its trillions of stars, this galaxy is not especially bright. Many of its stars are old and dim. There are few young, brilliant blue stars to light it up with youthful vigor. It is massive, yes, but subdued, like an ancient city long past its vibrant peak. Its period of rapid, explosive growth appears to be largely over. Most nearby galaxies susceptible to its pull have already been absorbed. Fewer remain within easy gravitational reach. The giant now rests in a kind of equilibrium, dominant yet undeniably aging. When astronomers study this celestial object, they are not merely measuring its size. They are, in essence, reading a cosmic history book, its pages written in starlight. The ages of the stars, their unique chemical fingerprints, and their intricate motions all reveal crucial clues about past mergers and long-vanished galaxies. This galaxy is not a single, unified creation. It is a monumental structure, meticulously assembled from the remnants of countless galaxies that once existed independently. Their original names are lost, their distinctive shapes are gone, but their stars still shine, now as integral parts of something unimaginably larger. And that, precisely, is what makes this object so profoundly important. It represents the extreme upper limit of what the universe can construct using gravity, time, and matter. It vividly demonstrates that galaxies are not fixed, immutable entities. They grow, they collide, and they continuously evolve. The Milky Way feels enormous when we contemplate its scale. But this cosmic titan forces us to expand our sense of scale once again, to push the boundaries of our mental picture. Because if the universe can build a galaxy millions of light-years wide and containing 100 trillion stars, then our conception of what is truly possible remains incomplete. And we have not even approached its most extreme part yet. At the very center of this immense, ancient structure lies something even more astonishing than the galaxy itself. Every large galaxy we know of harbors a supermassive black hole at its core. Our own Milky Way hosts one, famously named Sagittarius A star, weighing approximately 4 million times the mass of our Sun. That already sounds utterly enormous, 4 million suns compressed into a region smaller than our entire solar system. But the black hole residing within this galactic giant exists in a completely different category altogether. Astronomers estimate its mass may encompass tens of billions of times the mass of the Sun, possibly ranging between 40 and 100 billion solar masses. Pause for a moment, and allow that sheer scale to truly settle within your mind. If Sagittarius A star were the modest size of a coin, this black hole would loom as large as a towering mountain. If hypothetically placed at the center of our solar system, its event horizon, the terrifying boundary beyond which not even light can escape, would stretch far beyond the orbit of Pluto. Everything we consider our cosmic neighborhood would lie irrevocably inside that boundary of no return. And yet, black holes are not cosmic vacuum cleaners, indiscriminately pulling in everything around them. Their gravity behaves precisely like any other object of equivalent mass. If our Sun were replaced by a black hole of the exact same mass, Earth would continue its orbit almost precisely as it does now. The crucial difference lies in density. A supermassive black hole contains an unimaginable quantity of mass, compressed into an infinitesimally tiny region. Space and time themselves are dramatically bent and warped around it. The closer you approach, the stranger the laws of physics become. Near the event horizon, time slows down to a crawl relative to distant observers. Light curves along unseen pathways. Rays that once appeared straight begin to spiral inward, inexorably. Inside that chilling boundary, every single possible direction leads directly toward the center, toward the singularity itself. The black hole at the heart of this colossal galaxy did not begin its existence this way. Like the galaxy it dominates, it grew slowly, inexorably, over billions of years. Each time a smaller galaxy was absorbed, its own central black hole would have been inexorably drawn inward. Eventually, these two black holes would begin to orbit each other, forming a powerful binary system. Over immense spans of time, they would spiral closer together, radiating colossal amounts of energy in the form of gravitational waves, ripples in spacetime itself. When they finally merged, the cataclysmic result would be a single, even more massive black hole. This process, a series of cosmic collisions, may have happened dozens of times throughout its ancient history. With each merger, the central black hole gained immense mass. With each feeding event, it grew more powerful, more formidable. At certain points in its distant history, it was likely anything but quiet. When gas and dust fall toward a supermassive black hole, they do not immediately disappear. Instead, they form a rapidly spinning accretion disk around the event horizon. Friction and intense magnetic forces within this disk heat the material to extreme temperatures, causing it to glow with a brilliance that can outshine entire galaxies. In these active phases, black holes can launch enormous jets of high-energy particles into space, traveling at nearly the speed of light. These powerful jets can stretch for millions of light-years, carving vast, empty cavities into the surrounding hot gas of the galaxy cluster. Observations of the cluster enveloping this giant galaxy reveal precisely those kinds of cavities, immense bubbles in the hot gas, almost certainly inflated by past outbursts from the central black hole. For a time, it must have been one of the most energetic and violent objects in its entire region of the universe. But today, it appears relatively calm. There is no brilliant quasar blazing at its center, no intense feeding frenzy consuming everything in its path. The galaxy has largely exhausted the easily accessible supply of cold gas that fuels such dramatic activity. The black hole still dominates gravitationally, a silent, colossal anchor, but it now rests in a quieter, more subdued phase. It is like a dormant volcano that once reshaped the very landscape around it, now peaceful, but certainly not gone. The relationship between a galaxy and its central black hole is not one-sided, they grow together, intricately linked. The mass of the black hole is closely tied to the mass of the galaxy's central bulge. This suggests a deep, symbiotic connection. When too much gas begins cooling and drifting inward, the black hole can reheat it through energetic outbursts, thereby preventing new stars from forming. In this way, it acts almost like a cosmic thermostat, regulating the growth and evolution of its host galaxy. In a system as monumentally massive as this one, that powerful feedback mechanism may be the very reason why star formation has slowed so dramatically. The same black hole that grew through successive mergers may now be actively helping to keep the galaxy in a kind of stable, aging state. And then, there are gravitational waves. When supermassive black holes merge, they unleash unimaginable quantities of energy. Not in the form of light, but in ripples in spacetime itself. These waves travel outward at the speed of light, stretching and compressing space as they pass. In 2015, scientists first detected gravitational waves from merging black holes using the LIGO observatories. Those were stellar mass black holes, far smaller than the titanic giants found at galaxy centers. Future space-based detectors may one day observe the gravitational waves from mergers of supermassive black holes, like the colossal ones that built this cosmic giant. When that incredible moment arrives, we will not just see the universe, we will, in a profound sense, listen to it. And somewhere in the deep past, billions of years ago, such mergers almost certainly occurred at the very heart of this galaxy. Each collision would have been catastrophically violent, on scales we can barely imagine. Yet, from that violence, emerged stability. From that chaos, came structure. The black hole now sitting quietly at the center is the accumulated memory of those ancient, cataclysmic events. It is the immovable gravitational anchor of one of the largest galaxies ever discovered. And yet, even this monster is not eternal. According to the profound principles of quantum physics, black holes slowly lose energy through a process known as Hawking radiation. Over inconceivably long timescales, far, far longer than the current age of the universe, even supermassive black holes will eventually evaporate. For a black hole containing tens of billions of solar masses, this process would take a number of years so astronomically vast it defies any meaningful comparison. Trillions upon trillions of years, but not forever. Even the most massive object in this galaxy has an ending, implicitly written into the fundamental laws of physics. That startling realization fundamentally changes how we perceive it. The central black hole may feel permanent, indestructible, timeless. But like stars, like galaxies, like clusters, it exists within the broader, ongoing evolution of the cosmos. It grew from smaller beginnings. It powerfully shaped its surroundings. It now rests in a quieter, more stable state. And one day, in a future truly beyond imagination, it will finally fade. When we contemplate the sheer scale of this galaxy, it is easy to focus solely on the stars. 100 trillion points of light, spread across millions of light-years. But at its heart lies something even more concentrated, even more extreme, a region where gravity becomes absolute, an inescapable force. A place where space and time bend inward, impossibly. A cosmic engine that played an instrumental role in shaping the largest galaxy we have ever found. And this, astonishingly, is only part of the story. Because what we see, the stars and the black hole, may represent only a small fraction of what truly gives this giant its incredible mass. Most of it remains entirely invisible. When we gaze upon this enormous galaxy, we witness trillions of stars, an ocean of light that has journeyed for over 1 billion years. We see structure, intricately shaped by countless mergers and the relentless pull of gravity. But what our eyes perceive is merely a fraction of what truly exists there. Most of the mass holding this titan together is completely invisible. Astronomers call it dark matter. Dark matter does not glow. It does not absorb light. It does not reflect it. If you were to look directly at it, you would perceive absolutely nothing at all. And yet, without its pervasive presence, galaxies like this could not exist in their present, magnificent form. The first crucial clues to its existence came from observing motion. When scientists precisely measure how fast stars orbit within galaxies, they instinctively expect those speeds to decrease with increasing distance from the galactic center. This behavior mirrors planets in our solar system, which move more slowly the farther they are from the Sun. That is precisely how gravity from visible matter should behave. But that is not what they found. Stars positioned far from galactic centers move much, much faster than they should. Fast enough, in fact, that they should long ago have escaped into the vast emptiness of space, unless something unseen is adding powerful, extra gravity. That unseen mass is dark matter. In spiral galaxies like our Milky Way, dark matter constitutes roughly 85 to 90% of the total mass. The bright stars, the glowing gas, and the dust we can readily observe are merely the surface details, the luminous froth atop a hidden ocean. The true, foundational structure of a galaxy is built upon an invisible, gravitational scaffolding. Now, imagine scaling that up exponentially. If our galaxy resides within a massive halo of dark matter, then a galaxy 40 to 60 times larger must be cradled within something far, far greater. This giant is embedded in a dark matter halo that may extend tens of millions of light-years into space, stretching far beyond its visible stars. The luminous galaxy we observe, that brilliant oval of light, is only the bright core of a much, much larger, unseen structure. If you could somehow visualize dark matter, this galaxy would appear as a glowing knot, embedded within a vast, shadowy mountain of invisible mass. And that mountain is not isolated. It connects to an even larger, more encompassing structure. The galaxy cluster surrounding it, Abell 2029, is itself intricately wrapped in an enormous, pervasive halo of dark matter. Clusters are among the most massive gravitationally bound objects in the entire universe. Their dark matter scaffolding binds hundreds of galaxies together, like an invisible framework supporting luminous lanterns. This is the fundamental mechanism by which the universe builds on the grandest scales. Dark matter forms the very backbone of the cosmic web. After the Big Bang, minute density variations in the early universe caused dark matter to clump together first, forming gravitational wells. Ordinary matter, hydrogen and helium gas, then slowly fell into those wells. Stars ignited, galaxies formed, and clusters assembled. Without dark matter, the gravity generated by normal matter alone would not have been strong enough to build structures this colossal before cosmic expansion pulled everything irrevocably apart. In other words, this massive galaxy exists because of something we cannot see and do not yet fully comprehend. And that mystery runs incredibly deep. Scientists have been tirelessly searching for dark matter particles for decades. Underground detectors listen for faint, elusive collisions. Space telescopes meticulously scan for indirect signals. Particle accelerators attempt to recreate conditions from the early universe. So far, dark matter has remained stubbornly silent. We know it exists because of its unmistakable gravitational fingerprints, but we do not know what it is truly made of. And that means when we measure the total mass of this galactic giant, we are working with two distinct, profound layers, the visible and the invisible. The visible layer is staggering enough, 100 trillion stars, millions of light-years across. But the invisible layer may contain even more mass. Some estimates suggest the total mass of this system, including its dark matter halo, could reach into the hundreds of trillions of solar masses. That is not merely a galaxy, that is a gravitational titan. Now, step back even further, zoom out to the cosmic canvas. Galaxies do not float randomly in empty space. They meticulously trace out enormous filaments that stretch across the entire observable universe. Between those filaments lie vast cosmic voids, immense regions almost entirely empty of galaxies. If you could zoom out far enough, the universe would resemble a majestic three-dimensional spiderweb. Bright knots mark the galaxy clusters. Long, luminous strands connect them. And dark matter forms the underlying threads, the invisible scaffold. This galaxy sits precisely at one of those bright knots. It is not only monumentally massive in itself, it occupies a uniquely privileged position in the cosmic web. Over billions of years, matter flowed along invisible dark matter highways, drawn into this region. Smaller galaxies formed along those filaments and gradually drifted inward, feeding the central giant. Its location was perfect for relentless growth, like a deep valley at the meeting point of many cosmic rivers. And because of that, this galaxy was able to accumulate more mass than almost any other known. This brings us to a crucial realization. The astonishing size of this galaxy is not random. It represents the upper limit of what the universe can construct under the current, precise laws of physics. Gravity pulls matter together. Dark matter provides the essential scaffolding. Cosmic expansion pushes everything apart. Somewhere between those opposing forces lies a delicate balance. If gravity were stronger, perhaps galaxies would grow even larger, beyond comprehension. If cosmic expansion were faster, maybe they would never grow this big at all. The very existence of this galaxy tells us something profound about the fine, intricate balance of the universe. It shows us that the cosmos allows structures to grow to scales millions of light-years across, but not infinitely large. And there is something truly humbling in that understanding. When we contemplate size, we often focus on what we can see. But the universe constantly reminds us that the visible is only a small fraction of reality. The stars we admire, those twinkling points of light, are mere surface details on something far deeper, far more pervasive. This galaxy, with its trillions of suns, is supported by an invisible ocean of mass, an ocean we have not yet directly touched or fully understood. It forces us to humbly admit that our knowledge, while powerful and ever-expanding, remains incomplete. We can measure light that traveled for 1 billion years. We can calculate mass from the precise orbital motion of stars. We can simulate cosmic structure formation on supercomputers. And still, most of what holds the largest galaxy ever discovered together remains unseen, shrouded in mystery. There is profound beauty in that mystery because it signals that discovery is far from finished. This giant does not represent the end of understanding, it represents a magnificent frontier, a boundary between what we know and what we are still diligently learning. When you picture this galaxy now, do not imagine only a glowing oval of ancient stars. Imagine an immense, invisible halo of dark matter surrounding it, stretching for millions of light-years. Imagine gravity shaping matter across those colossal distances. Imagine dark matter forming a colossal scaffold, upon which 100 trillion stars were hung like myriad lights on a vast, cosmic frame. The largest galaxy we have found is not just a triumph of scale. It is a powerful reminder that most of the universe is hidden from direct view, and that even in the face of something so monumentally massive, we are still only seeing the luminous surface. When we speak of this enormous galaxy, it is easy to focus solely on its sheer size, the millions of light-years across, the trillions of stars, the central black hole weighing billions of suns. But there is another dimension, just as staggering as its physical scale, and that is time. The light finally reaching our telescopes today began its extraordinary journey more than 1 billion years ago. That means we are not seeing this galaxy as it exists now. We are seeing it precisely as it was in Earth's incredibly distant past. 1 billion years ago, our planet looked nothing like it does today. There were no towering forests, no animals walking on land, no familiar ecosystems. Life was simple, mostly microscopic, confined to the ancient oceans. While evolution slowly unfolded its intricate design here, photons were leaving distant stars in that galaxy, beginning an epic journey across intergalactic space. They traveled through unimaginable darkness at 186,000 miles per second, crossing unfathomable distances without slowing, without stopping, carrying with them an indelible record of their origin. Only now, after eons, have they finally arrived. In astronomy, distance is inextricably inseparable from time. The farther we look, the further back in time we see. Every distant galaxy is a perfectly preserved memory of the universe at an earlier stage. This giant system, sitting more than 1 billion light-years away, is a haunting snapshot from a cosmic era long, long gone. And that raises an unsettling, yet profoundly fascinating, question: what does it look like today? Over the last 1 billion years, countless stars inside it have lived out their lives and perished. Some may have collapsed into new black holes. Others may have merged. Perhaps another galaxy has drifted inward and been irrevocably absorbed. Perhaps the central black hole has experienced new, violent bursts of activity. We simply do not know, because that crucial information has not yet reached us. Astronomy, in this profound way, is a form of cosmic archaeology. We painstakingly reconstruct history from ancient light. Now consider the sheer physical distance itself. A single light-year is approximately 6 trillion miles. Multiply that by 1 billion, and you begin to approach the unfathomable gulf separating us from this galaxy. Even our fastest spacecraft would be hopelessly, tragically inadequate for such a journey. Voyager 1, traveling at roughly 38,000 miles per hour, would take tens of thousands of years just to reach the nearest star. To cross our own galaxy at that speed would require billions of years. To cross this giant galaxy would take longer than the universe itself has existed. Even light, the fastest entity in existence, requires millions of years to travel from one side of this behemoth to the other. If there were civilizations residing on opposite edges of this galaxy, a message sent at the speed of light would not arrive for several million years, and a reply would take just as long to return. Communication across a single galaxy would unfold on geological timescales. This is the mind-bending scale of separation we are contending with. And yet, within that vastness, stars still shine, planets may still orbit, and time continues its relentless, silent passage. Now let us look forward, rather than backward. This galaxy, despite its monumental size, is not young. Most of its stars are incredibly ancient. The brilliant blue stars that burn quickly and die young have largely disappeared, their brief, fiery lives long since extinguished. Star formation has slowed dramatically because the cold gas required to create new stars has mostly been used up or heated beyond the point where it can collapse under its own gravity. In many ways, this galaxy has already entered a mature, perhaps even elderly, stage of its incredibly long life. Over the next tens of billions of years, its remaining sun-like stars will expand into bloated red giants before shedding their outer layers and shrinking into dense white dwarfs. Smaller red dwarf stars, which burn their nuclear fuel slowly and efficiently, will continue shining for trillions of years. These dim, persistent stars will be the very last lights to flicker out, long after brighter stars have faded into oblivion. But even red dwarfs do not shine forever. Eventually, star formation across the universe will cease entirely. Gas will become too sparse, too diffuse to collapse into new suns. One by one, stars will exhaust their precious fuel. The galaxy will dim gradually, not in a dramatic collapse, but in a slow, quiet, inevitable fading. What will remain after that is a desolate collection of stellar remnants, white dwarfs, neutron stars, and black holes, silently drifting through a darkened, ghostly structure. At the very center, the supermassive black hole will persist far, far longer than any star. Its gravity will continue to shape the motions of whatever remains within its fading empire. Yet, even that colossal object is not eternal. According to quantum theory, black holes slowly lose energy through the elusive process of Hawking radiation. Over incomprehensibly long timescales, numbers so astronomically vast they barely fit into mathematics, this central black hole will eventually evaporate. Not soon. Not in billions or trillions of years. But eventually. The largest galaxy we have ever discovered will not last forever. It exists within a finite window of cosmic history, just as we do. There is something quietly profound in that realization. We live at a time when galaxies still glow brightly, when stars are abundant, when distant clusters are still visibly blazing across billions of light years. In the far, far future, cosmic expansion will carry many galaxies beyond the observable horizon. Observers living trillions of years from now might see only their local galactic structure, completely unaware that a universe filled with trillions of galaxies once surrounded them. Right now, in this luminous moment, we are fortunate. We can look outward and see the universe in its incredible richness and astonishing variety. We can detect a galaxy millions of light-years across and measure its properties with surprising precision. We can calculate its distance, estimate its colossal mass, and reconstruct its ancient past. And in doing so, we confront something truly extraordinary. Even the largest structures built by gravity are temporary. They are assembled slowly, meticulously, over billions of years. They shine for a time. And then, inevitably, they fade. This giant galaxy is not just an object in space. It is a moment in the long, unfolding story of the cosmos, a monument to what gravity can build, and a poignant reminder that even monuments eventually erode. In the final section, we step back from the dizzying numbers and ask a deeper question. What does the existence of something this vast, this ancient, truly mean for us? When we step back from the numbers, the millions of light years, the trillions of stars, the billions of solar masses, we are left with something far deeper than mere statistics. We are left with profound perspective. The largest galaxy we have discovered is not just a record-breaking object. It is a powerful statement about what the universe is ultimately capable of building. It is gravity, given immense time. It is matter, given infinite patience. It is the slow, relentless assembly of structure over billions of years. And yet, despite its monumental size, it follows the same fundamental rules as everything else. The same gravity that pulls an apple toward Earth shapes galaxies. The same atomic physics that powers our sun powers its stars. The same elements found in our bodies, carbon, oxygen, iron, exist in its distant, ancient suns. There is no special set of laws for the large, and another for the small. The universe scales upward, meticulously using the very same blueprint. That profound realization changes how we see ourselves. When you hear that a galaxy contains 100 trillion stars, it is natural to feel incredibly small. Our planet becomes a minuscule dot. Our species becomes a brief, flickering light. Our lives, measured in mere decades, seem insignificant next to billions of years of cosmic evolution. But there is another, more empowering way to look at it. The very atoms in your body were forged inside stars. Long before Earth itself formed, earlier generations of massive stars fused hydrogen into heavier elements and scattered them throughout space in cataclysmic supernova explosions. Those recycled elements eventually became part of a cloud of gas that collapsed to form our sun and planets. In other words, the very same processes that built that distant, colossal giant also built you. The universe did not create galaxies and then, separately, create life. Life emerged from within galaxies. We are not outside observers of the cosmos, we are an intrinsic product of it. When we look toward that enormous structure, more than 1 billion light-years away, we are, in a very real sense, looking at a distant relative, another magnificent expression of the same cosmic chemistry. And there is something even more remarkable. That galaxy does not know we exist. Its stars burn. Its black hole rests at the center. Its structure slowly evolves. It is utterly indifferent to our fleeting presence. But we know it exists. On a small, rocky planet, orbiting an average star in an ordinary spiral galaxy, a species evolved the astonishing ability to ask profound questions. We built telescopes. We developed intricate physics. We learned how light travels and how gravity behaves. We decoded the faint signals arriving from across intergalactic space. And from those signals, those whispers from the deep past, we meticulously reconstructed something unimaginably enormous. That is truly extraordinary. In a universe filled mostly with invisible dark matter and silent radiation, with empty space stretching between islands of stars, consciousness has miraculously emerged. Matter has arranged itself in such a way that it can reflect on its own cosmic origins. When we measure the size of the largest galaxy ever discovered, the universe is, in a profound sense, measuring itself. This perspective does not shrink us, it profoundly connects us. The story of that galaxy is also the story of hierarchical growth, the fundamental idea that small things combine to form larger ones. Tiny fluctuations in the early universe grew into clumps of dark matter. Gas fell into those clumps. The first stars formed. Small galaxies merged into larger ones. Larger ones merged into colossal giants. The precise process that created that enormous elliptical galaxy is the very same process that shaped our Milky Way, and the same process that will eventually merge the Milky Way with Andromeda. We are not merely spectators to cosmic evolution, we are active participants within it. Even our galaxy is slowly absorbing smaller neighbors right now. Streams of stars in our night sky are the ghostly remnants of dwarf galaxies, torn apart by the relentless pull of our gravity. In billions of years, our galaxy will likely collide with Andromeda, reshaping both into a new, larger structure. In that sense, the giant we have been discussing is not an alien, isolated phenomenon. It is an extreme, awe-inspiring version of something happening everywhere, constantly. It shows us the ultimate endpoint of accumulation. It reveals what can truly happen when gravity is given enough time and enough raw material. But it also reveals inherent limits. Galaxies do not grow forever. Cosmic expansion stretches space. Dark energy accelerates that expansion. Eventually, galaxy clusters become isolated islands in an ever-expanding void. New material stops falling inward. Growth slowly, inexorably slows, and then stops altogether. Even the largest galaxies reach a kind of final, mature form. The existence of this giant tells us something profound about balance. Gravity pulls matter together. Cosmic expansion pushes it apart. Dark matter shapes the invisible framework. Ordinary matter lights up the resulting structure with countless stars. Somewhere within that delicate balance lies the maximum size a galaxy can ultimately achieve. And we are incredibly fortunate enough to live in an era when we can actually perceive it. If intelligent beings exist within that galaxy, and we do not know if they do, their night sky would look dramatically different from ours. They would see a dense, bewildering scattering of ancient stars in every direction. They might not see graceful spiral arms. They might not see a bright band of stars crossing their sky. Their entire view of the cosmos would be profoundly shaped by their location inside a giant elliptical system. But perhaps they, too, would look outward. Perhaps they would detect other galaxy clusters in the distance. Perhaps they would measure red shifts and discover the startling reality of cosmic expansion. Perhaps they would ask the very same questions we ask: how did this begin? How large is everything? What is our place within it all? It is entirely possible that somewhere among those 100 trillion stars, minds are wondering about the universe, just as we are. And from their perspective, our Milky Way would be just another faint spiral among countless others. That profound symmetry is humbling. We are not at the center. We are not in the largest structure. We are not in a privileged location. We are in one galaxy among trillions, orbiting one star among hundreds of billions. And yet, we are capable of understanding galaxies millions of light-years across. That is not small. The largest galaxy ever discovered stretches human imagination to its absolute limit. But the astonishing capacity to imagine it, to measure it, to model it, to comprehend it even partially, is equally astonishing. In the end, what makes that galaxy truly extraordinary is not only its mind-boggling size. It is what it reveals. It reveals that the universe is capable of building structures on scales that utterly dwarf human intuition. It reveals that the same simple, elegant laws of physics can generate astonishing, complex beauty. And it reveals that we live in a brief, luminous chapter of cosmic history when such magnificent structures still shine brightly enough to be seen. One day, far, far in the future, galaxies will fade, stars will burn out, the universe will grow darker and quieter. But right now, in this precious moment, we can look outward and see giants. And in seeing them, we expand not just our knowledge, but our profound sense of belonging in something far larger, far more ancient, than ourselves. The biggest galaxy ever discovered is larger than imagination itself. But the fact that imagination can reach that far, that, perhaps, may be the most powerful discovery of all.